Friday.
Okay, welcome class. It is Thursday, but it's the last day of the week. This is 9th period. Last Friday, we had an excellent lesson in which, Tyler, we took a function which does not have an antiderivative, thus the FTC is not applicable, and we said, damn, how are we going to do this integral? Answer math 9, but it's not really an answer. What?
That's a stale meme.
Therefore, Tyler, talking to you, good. How are we going to do it? We're going to use math 9, but how does math 9 work? Answer, oh, maybe they just use the RAM. And the conclusion was, no, they don't just use RAM, because in order to get accuracy, you need like a really massive amount of rectangles, and it becomes computationally like impossible. Is everyone, give me some head nods if this is all like coming back in your brain.
Head nods are
Good.
vigorous.
So period 3 and 4, which is watching this video right now, will have just seen this lecture, and they will have done at this point a worksheet which you had to do today for homework. Please take it out. Let's see what Miss Calculus got. She got rounded to 3 decimal places. L20 was 4.739, correct? Is that right? Maya, what happened? Okay, did you guys all get that number too? 4.739. And by the way, is that an underestimate or an overestimate? Underestimate, why?
Because geometry.
Is that because arctan is increasing on the interval 1, 5? Since arctan is increasing, everyone picture the picture in your head. LRAM is going to be an underestimate, agree? Okay, RRAM is going to be an overestimate, again because the function is increasing. She got 4.856. Beautiful. Confusing. T20, the trapezoid rule with 20 equal width subintervals gave 4.800, she says. You agree?
Oh, it's close enough.
Okay, close enough.
No.
You got 4.799?
I got 4.797.
Yeah, 798.
No, wait. Oh wait, maybe I might have messed this up. Yeah. Sorry, it is 4.798. You did a little swap. Yeah, 4.7. It is 4.798 for the trapezoid rule, T20. And is that a underestimate or overestimate?
Underestimate.
Underestimate because
Because it's concave.
arctan is concave down, so clearly the trapezoid is like living underneath. Okay, M20 is, Chris says 4.799.
Yeah.
Alice says 4.800. Anyway, it's one of those two. I guess if you're rounding to the nearest tenth, then it would be 4.800.
Yeah.
Or 1,000. And this one is a little bit more subtle. Is this going to be a underestimate or overestimate?
It's an overestimate because it's concave down, but I couldn't explain it to you.
So like
It is an overestimate because, did you watch the 5-minute video that I recorded after last Friday afternoon that you were supposed to watch for homework on Monday? Yeah, that's why you don't know.
But I do kind of know.
But you kind of know. Do you guys know what video I'm referring to?
Yeah.
If you're in period 3 or 4, you just watched it like 5 minutes ago. Good. We'll talk more about that later. All right. So all of that lecture was like background knowledge to what we're about to do now. Okay, take out your calculator. Can someone be the official MyGV calculator? Can you be the calculator person then? Turn on the TV, put it on TV video, grab the calculator over there by the pandas, and let's begin. Alright, I would like to take the integral.
Kevin.
I would like to take the integral from 0 to 2 of sine of x squared dx. So everyone please jump. Wait, no time. I'll deal with Maya. You deal with taking out your own calculator, typing this function into y1, getting a picture of what this function looks like on the interval 0, 2, and also possibly cheating by using math 9 or writing that off to the side.
So it's actually 1.
Oh no, not this crap again.
What do you mean this crap again?
It's like, no, I'm thinking of something else.
Okay, don't worry about it. Can you clear the memory? And then type sine of x squared. Okay, would someone like to quickly give me the actual answer using math 9?
Wait, do you want me to actually?
Yeah, reset. Alright. And Alex, you need to do multiple back and forth between the board and the thing. Okay. So we're taking the integral from 0 to 2 of sine of x squared dx. What shall we do? What we would like is to, did you grab it?
Oh, sorry.
What's the integral? Chico. Can you do a calculator? Okay,
0.805.
you have to like get one and bring it to that.
0.805.
What is it?
0.805.
0.805 says Serco. Okay, so let's just like put that in a box of like, I didn't know that. So like, I'll just write like secret, because I don't want to rely on Math 9, I want to do my own investigations. Well, here's what I would like to do. Someone make a suggestion of how we're going to do this. What should we do? LRM, RM, T,
How about the midpoint rule?
T, midpoints? Okay, but I'm not just interested in the midpoint rule per se. What I'm interested in is finding out not just the estimate, but how good my estimate is. And so, as you saw with that homework assignment that was due today, Kevin, because we did L20 and R20, and I know by calculus reasoning that one is an underestimate and one is an overestimate, that means I know for sure that the value lies between those two, yeah? And on the bottom, I got an even better estimate, right? Because I got 4.798 and then I got 4.799. That's really good because I knew that the trapezoid rule and the midpoint rule were respectively, whichever one it is, underestimates and overestimates. So we should
Find the derivative.
Yes, Chris is thinking ahead and he is saying, before I can find upper and lower bounds for the true area under this curve, I must analyze the increasing, decreasing concavitiness of this thing. Follow?
What?
And can we get a picture, Maya, of what this graph looks like so we know what to expect?
I'm trying, but I accidentally
Oh.
changed the, you know what, like why
That was an
SCL should be.
Y scale should be like
Right?
One.
Yeah, make them one. Take one.
If you have like 41 and 37, it should
Oh,
be
no.
1 to 1.
You're fixing the same.
Wait, we're going too slow. So, someone quick take the derivative of this function, back me up. So what is the derivative?
2x cosine x squared.
Yeah, it sure is. 2x, no, yeah.
Yeah.
2x
So,
cosine x squared. That's the derivative. We should take maybe like the second derivative too. While we're at it, what is the second derivative? The first times the second plus the first times the derivative of the second. So that would be like negative sine of x squared, but like then back in second. Did I even do that right?
Don't you need to?
Yeah, that's right. Yeah. So the second derivative is like 2 cosine of x squared minus 4x squared sine x squared. Okay. So generally I'm not in love with this. Also, can we just like look at the terrible window? I want to go from 0 to 2.
Okay.
Too slow, too slow. Everyone look at your window. What are you noticing about this function? Is it concave up or concave down on this interval?
It's both.
It's both. Are you as sad as I am?
A little bit.
Yeah, because why, Chris?
Like it means that we can't. In order to like know about it, we need to split it up into different segments.
Yeah. So I'm just really sad. The only approach I can possibly think of right now is to divide and conquer. But I really don't want to do this. So I did some math and I found that this function is concave up on the interval from 0 to 0.808. Does that look kind of borderline right? If you look at Maya's graph up there now in a nice window, doesn't it look like it's concave up until a point which is around 0.8? I see like a roughly point of inflection there. And then it's concave down on the interval from 0.808 to like 1.81 or some crap like that. But then it becomes concave up again on the interval 1.81 to 2. So I'm just like really sad. Because if I truly want an upper bound and a lower bound on this, then I'm going to need to split this up into intervals in which it's concave up, use like trapezoid, then midpoint, split, and then do that for each interval. So I don't want to do that at all.
Wait,
Okay.
just find which one is
Okay.
more.
So, new approach. New approach. The new approach is to somehow theoretically calculate how much error we're going to expect.
Crap, this is some statistics. So.
I don't think it's statistics. It is error analysis. Okay, so let's start with the easy case. Let's do LRAM. Just qualitatively, when do I expect LRAM to give me lots of error, and when do I expect LRAM to give me not so much error?
When it's like really steep, you should have a lot of air.
Yeah.
The closer the slope is to 1, the less area you should
If
have.
it's a
Oh,
really,
wait, no, what am I saying?
if it's a
It's when it's
really, if it's a really chill function, like so, then using, and I want to go from like here to here, then using LRAM, not so bad. It's still kind of bad, but it's not terrible. You guys with me? So this is okay. But, says Perry Beamer essentially, if the slope of the graph is big, and I want to go from here to here, and I want to use LRAM, then it's like pretty bad. And this is leading to more error. Who is with me? Yeah. Okay, good. Okay, so it seems that it is in fact the slope of the graph, or the derivative of the graph, which is kind of predicting how much error I should expect when using it, and that's exactly correct. Big derivative, big error. And the amount of error is related to the size of the derivative. Okay, so let's look at a particular function. So here's what I want to do. So the goal is I want to take the integral of some function on the interval from a to b. So I want to take the integral of some function. Alright, and I want to know what it is, and I want to know how much error to expect. Just suppose that on this interval, the biggest the derivative ever gets is some number, let's call it k1. So suppose that the size of the derivative, and I put absolute values because plus or minus, who cares, is less than or equal to some number k1 on the interval a to b. So never mind how you know that. Possibly you know that because you took the derivative and then took the second derivative to analyze the first derivative and found where the first derivative was maximum. Okay, maybe then you just round it up to the nearest number. Or suppose someone just tells you, this function never grows faster than k1 on this interval. Okay, well if that's the case, then what I have here is some kind of a picture. The picture looks like this. Here, what I'm going to do is I'm going to look at a particular subinterval. So let's look at the ith subinterval. So maybe like A is over here and B is over here. But what I'm now going to do is I'm going to look at the ith subinterval. So what does the ith subinterval look like? It's bounded by, let me make the picture bigger. It's bounded over here by x, this is x sub I, this is x sub I minus 1. And I probably need to introduce a little bit more facts here. So we're taking the interval from A to B. We're going to use n subintervals. And if we're going to use n subintervals, what is delta x, the width of each subinterval? We're going to do equal width subintervals. Oh, it sure is b minus a over I. Okay. And what we're now going to do is we're going to work on this assumption that this function has an upper bound on the size of the derivative. So let's just take some point over here, and let's just let that be the value of the function at the left endpoint of the ith subinterval. What can you tell me about the value of the function at the right endpoint of the ith subinterval? Based on the fact that the derivative is capped at k1. Right? So lots of things could possibly happen to this function on this subinterval. Perhaps this function is a constant. Perhaps this function is linear. Perhaps this function is doing some other crazy things. But what do I know about how much this function changes on this interval?
Never changes more than
It will change no greater than the linear representation using k sub I.
Well, the
What is, if the rate at which this function is allowed to grow overall is capped at k1, right? This is the speed limit of this function, right? The speed limit of this function is k1. How much could this function grow at most? At most, it could grow at k1 the entire subinterval. And so the biggest we're going to get is like a line with slope k1. Follow? Or it's possible that the thing looks like that. Okay, so it's kind of weird here because what's happening is, so we have three different pictures to draw. and thus we need sort of three different colors. There is our estimate using LRAM. Then there's what we know to be the biggest that function could grow, and then there's the function itself. Okay, what is the function actually doing on this interval? Well, that, unfortunately, I do not know. I do not know what this function is doing on this interval. So this is like, red is like the actual function. It is unknown to us, right? Because, yeah. What I am doing, however, on this interval, when I am using LRAM, is I am estimating that the area under the curve is determined by the value of the function at the left endpoint, right? So the green, is everyone with me? I'm kind of going maybe over-explaining this. The green rectangle is what I'm counting. The actual area is under the red rectangle. What I want to know is how much error could I be having at most? And what's the answer?
It's K times xi minus x of I.
Yeah, it's like the area of this blue triangle. The area of this blue triangle, this represents the max possible error. In other words, at worst, this function might be this purple function. And I'm pretending that this function is constant. Ultimately, that's what LRAM does, right? LRAM pretends all functions are like constant functions. But in fact, the function might be growing. So how much error did I make on each subinterval? I made that much error. Okay, what is the area of this? What is the area of this blue triangle?
So it's delta x.
Well, it's delta.
It's basically 1/2 delta x times, what is this height?
That is x of I minus x of I minus 1 plus k of I times dx. The slope is the change in y over change in
Yeah,
x.
so this line ever says this line, this purple line has slope k1, right? Because ultimately the purple line is like my worst nightmare, right? The purple line is how fast this function might be going. It's how fast the function might be growing if it is allowed to grow at its max. That's going to give me the most possible error relative to the fact that I'm pretending the function is constant. So if the slope is k1, but my function has increased by, or if I've gone over by delta x, then how much have I gone up by?
Delta x.
Delta x k1, right? This is k1 delta x. Because like the change in y is just delta change in y over change in x times delta x. Is everyone okay with that? It's like algebra 1. Okay, therefore, the area of this blue rectangle is 1/2 delta x times k1 delta x. Okay, so what does that represent? That represents, so we can write this. So what I've just shown is that on each subinterval, if indeed the derivative is bounded by k1, then the maximum error is that. It's 1/2 k1 delta x squared. I could produce that much error, at most, on each subinterval according to this thing. Okay, so for the entire integral, from a to b, question is how much total error was made, at most? How much total error is there? At most.
Isn't it just
1/2?
Yeah, 1/2
times
That times.
Yeah. B minus A.
That times n.
I think it's just that times n, right?
Yeah.
Yeah, because this is the error on each subinterval.
Oh.
So the total error is just the error on each subinterval times the number of subintervals. So the total error is going to be, it's going to be 1/2 k1 times delta x, which is in reality b minus a over n, squared times n. Which reduces to k1 over 2 b minus a squared over n. Okay. Alright. This is an awesome formula. Let's dwell on it for a minute. What does this formula represent in words? Shushan, in words, what does this formula represent?
It's like the maximum error you could get when you're like trying to find the integral using numerical integration.
Yeah, that's exactly right. He says it's the maximum error that we might have for a particular integral, given that k1 is the rate at which the derivative grows, and we have n subintervals. Yes.
It's more like the error if you're using
L.
something that's completely linear.
Mr. Rose,
Yeah.
can I get a drink of water?
Yeah. Okay.
It has to be completely linear for that amount of error to occur.
Yes. The function, right. What he's saying is, if you're using LRAM, when do you get the most possible error? You get the most possible error. Well, it's a little complicated. For a given k, then the most error will result from the function just growing at rate k the entire time.
Yeah, wait. The function itself doesn't have to be linear, right?
No, the function doesn't have to be linear. The function might do crazy things, right? I mean, there are certainly functions which will give you more crazy error than linear functions. For example, we did this function e to the x squared in the last video, right? That grows so fast, right? That's going to give you lots of error using LRAM, but that will be taken care of by the fact that the derivative is also quite big there, so we're going to have a quite big k. Okay, so wait, let's make some observations about this formula. One observation you might make about this formula? Yeah.
That'll also work for RM, right?
Okay, yeah, also for RM it's the same thing. Yeah, let's go through each letter in this formula and explain how it affects the total error. Give me one, Mia.
K1 is the maximum change because if it like changes more, it's gonna have more.
Exactly. Yeah, good. She says the bigger K1 is, the more error. And she also gave an explanation for why that makes sense. Because if your function, she says, if the function has a quite large derivative on that interval, then it means the function's changing very rapidly, and we would expect LRAM to give a lot of error, right? So the smaller the cap is on how fast the function is growing, the less error we should expect, and the bigger the cap is. Follow? Okay, Chico, give me another one. Well, then you're mumbling and rambling, and I didn't hear you. We're trying to understand this formula better by looking at each facet of it and talking about how it affects things. So what does n do? What does that mean, and how does n affect the error formula? N is the number of subintervals, true. Wait, hold on. Someone help him. Shushan.
The bigger n is, the smaller your error is.
Yeah. Exactly. That's all. Yeah. The bigger n is, the less error. Which makes sense, right? That's like duh, right? The more subintervals, then the more often we're sampling what the function is doing, so we should expect less error. And that's exactly what the formula bears out, right? As n gets larger and larger, the error gets smaller. And there's one more. Kaylin.
I guess B and A.
Yeah.
The closer together they are, the less error.
The less error, yeah. I think it makes sense to talk about it the other way, right? The bigger B minus A is, in other words, the wider the interval over which we're integrating, then of course we're going to get more error. The more error. Because, and again, I think that makes sense, right? Because we're going to get a certain amount of error per subinterval. Then, the longer we integrate, the more the error grows. Cool? How are we feeling about this? Okay, good. Let's do an example of this. here is the kind of example that I think that makes a lot of sense. So take the integral from 1 to 6 of 2 sine 3x dx. Okay, so do you want to cheat and get the real answer first, real quick? Let's do that. Okay, let's cheat and math 9 it, but we're gonna say, like, we're gonna whisper it. Also, we're gonna write it on the board and but we're gonna pretend that we don't really know.
You promise after this, you'll always be able to use a calculator?
Negative 1.100, etc. Okay, great. All right, but I don't want to use Math 9. I want to program Math 9 type analyses. So here's our task: find L30 and give a bound on the error. And give a bound on the error.
If you knew, like, if you did L30 and R30 and you knew one was like an overestimate and one was an underestimate.
Okay, he's saying good things. He says, yo, can I do the old thing, which is just take L30 and R30 and then just know that it's somewhere in between? Why does that not work in this case? I know, but why does that not work in this case?
So it's giving you a bound on values, not a bound on error.
Well, also, this function has like period, like 2 pi over 3 or something, which is like not that much, which is like about 2, right? So on the interval from 1 to 6, this function's going up and down and up and down and up and down. So it's certainly not just increasing or just decreasing, right?
Yeah.
Yeah.
But if you knew the bound for like L30 and R30 and you knew like the difference.
Well, once you have a bound, you just have a bound. Let's just do it. First of all, everyone just do L30 real quick, just like review. So basically estimate the area under the curve with 30 subintervals using LRAM. But now the new thing is, in addition to finding L30, I can tell you by how much we're off by at most. So delta x is like 1/6, yeah? What'd you get?
Yep.
I think I got something different, but I could be wrong.
No, I think I read the new one. So it's 1/6 times
Yeah, it's gonna be 1/6 times the sum from I equals 0 to 29 of the function. It helps to just type the function into y1. It's like really helps math.
What?
You just type the function into y1. And then we're integrating from 1 to 6. So I don't know what the function looks like, or I do, but I don't care at the moment, so I'm just going to draw like a generic. So the first subinterval is going to have left endpoint right at 1, and then each time I skip by 1/30th, right? So that's like 1 plus 1 over 30, and that's 1 plus 2 over 30, etc., etc. I'm doing this right? No, 1/6. Skip by 1/6 each time. 1/6 plus 2/6, until all the way I get to 1 plus 36, which is 6. But actually, I never used that one, right? The last rectangle has height. Skip by 29.
Wait, so it's more one.
So it's f of, you guys back me up here, it's going to be f of 1 plus 1/6 I. Agreed? Okay, Sarah agrees. So yeah, so your expression should be y1 of 1 plus 1/6 x, variable x. But I want to start at 0, since it's LRAM, right? And then I end at 29, because we're doing L30. And step 1, so just paste. Boom. Okay. So, good. That is what I got. So L30 is negative 0.9285. Okay, congratulations. That's the kind of crap that we did last class. But this class, I am now going to produce a bound on that error. Because it's not worth it to just know what we think the answer is. We also want to know how much we're off by. Every estimate, Stein makes this joke, I'm kind of ripping on this joke. Giving an estimate without a bound is ridiculous. For example, I have $1 million, approximately. That is not a lie, Fausto. I do have approximately $1 million. The real follow-up question should be,
Approximately how close?
approximately, yeah, how much error is there in your estimate of how much money you have? Well, the error is about plus or minus $980,000. Okay, so I have about $1 million plus or minus $980,000.
Really plus.
Okay, good. So, good. The point of that stupid example is that, right, an estimate is worthless without a bound on how, without also telling the person how much you could be off by at most. Okay, do we know some facts about the function 2 sine 3x? Like every, ooh, I love that answer. Ever says, I know everything you would ever possibly want to know about this function. In particular, what is it that we're interested in right now? The derivative. What is the derivative?
6 cosine.
It is 6 cosine 3x. How much do you know about 6 cosine 3x?
I know the max.
Also, everything literally there is to know about this. So what can I say about this derivative on this interval?
The max is 6.
The max is 6. Okay, so I now make the following claim. The derivative, for sure, is less than or equal to 6. On the interval, on the interval to 1, 6.
That becomes K1.
That becomes K1, right? Once you have an upper bound on the derivative, which you can do for known functions, then we can use that in our error formula. Okay, so how much error should we be expecting? Have you guys done that yet?
Yeah, take 5, 6.
So what is the max error? The max error is, according to that formula, it's K1, which is 6 over 2 times the width of the interval, which is 5 squared, over the number of subintervals, which is 30. And now, like, some math happens, and we get, what is that? 5, 6, 15 sixths? No, what?
5, 6.
5 sixths.
Wait,
Yeah.
No.
No.
5, 2.
No.
5 over 2. Or
Yeah.
2 or 5.
Yeah, 5
You
halves.
need to do fractions.
no, 5 over
5
2.
sixths. 15 sixths. 15 sixths. Which is,
Wait.
I still screwed
Wait.
up. 15 sixths, which is just 5 halves.
Yeah.
Which is what you guys were all saying. Okay, that is a quite terrible bound. Here's what I'm now prepared to say. Here's I'm submitting this to my engineering boss. Well, this integral is negative 0.9285 plus or minus 2.5. Okay, does everyone realize why that's terrible, right?
Because it's more than the actual.
Yeah. Okay, can we do better?
I hope so.
We should be able to do better. So the kind of question is that you now might ask is, how many rectangles are required